Bismillahirrahmanirrahim. Assalamu alaikum students. I hope you all are doing well. In previous lecture we had completed our discussion on the different types of drug release systems. In today's class we will be starting our discussion on the types of the formulation used in sustained and controlled release drug delivery systems, that is matrix formulation and reservoir formulations. Matrix systems or reservoir systems can be used to formulate drugs into controlled and sustained release drug delivery system. So let's begin our discussion with the matrix formulations. In case the physicochemical properties of the drug are not suitable for development of a suspension formulation, the drug can also be incorporated into a carrier matrix. In the carrier matrix, the drug is dispersed either molecularly or as a solid drug particles. The release rate is controlled by the dissolution rate of the drug in the carrier matrix. In case the carrier matrix is also biodegradable, the release rate is also controlled by the degradation rate of the matrix. अगर फिजिको-केमिकल प्रॉपर्टीज़ ड्रग की सूटेबल नहीं हैं फॉर डेवलपमेंट इनटू अ सस्पेंशन फॉर्मुलेशन, तो ड्रग को हम एक कैरियर मैट्रिक्स के अंदर भी इनकॉर्पोरेट कर सकते हैं. कैरियर मैट्रिक्स में ड्रग को हम डिस्पर्स कर सकते हैं इधर मॉलिक्यूलरली या फिर सॉलिड ड्रग पार्टिकल्स की फॉर्म के अंदर. रिलीज रेट ड्रग का डिसोल्यूशन रेट ऑफ ड्रग के साथ कंट्रोल होता है इन केस ऑफ दी कैरियर मैट्रिक्स. अगर ड्रग को आप कैरियर मैट्रिक्स के अंदर कन्वर्ट करते हैं तो ड्रग का रिलीज रेट कंट्रोल होता है बाय द डिसोल्यूशन रेट ऑफ द ड्रग. इन केस कैरियर मैट्रिक्स के अंदर अगर आप बायोडिग्रेडेबल पॉलीमर्स यूज़ कर रहे हैं तो रिलीज रेट इज़ ऑल्सो कंट्रोल्ड बाय द डिग्रेडेशन रेट ऑफ द मैट्रिक्स. Matrix drug delivery system. In a matrix or a monolithic drug delivery system, the drug is either molecularly dissolved or dispersed inside a matrix that we had previously discussed. Compared to a reservoir system, a matrix system is not enveloped within a rate limiting membrane. As such, the release rate of the drug from the matrix system is normally not constant and decreases in time. In literature, various types of matrix systems are described. In principle, they can be categorized in diffusion based designs, which are homogeneous matrix or porous matrix, dissolution based designs, and erosion based designs, which could be bulk erosion or surface erosion based designs, and a combination of diffusion or dissolution based designs. ड्रग को हम मॉलिक्यूलरली डिज़ोल्व करते हैं या डिस्पर्स करते हैं मैट्रिक्स सिस्टम के अंदर. इस मैट्रिक्स सिस्टम को मोनोलिथिक डिलीवरी सिस्टम भी कहते हैं. मैट्रिक्स सिस्टम में ड्रग एनवेलप नहीं हो रही है इनटू डोजेज फॉर्म या कोट नहीं हो रही है जैसे कि हम रिजर्वॉयर सिस्टम के अंदर एक रेट लिमिटिंग मेम्ब्रेन में ड्रग को कोट कर रहे हैं. मैट्रिक्स सिस्टम में रिलीज रेट ऑफ ड्रग इज़ नॉर्मली कांस्टेंट और ये डिक्रीज़ होता रहता है बाय टाइम. मैट्रिक्स सिस्टम को हम डिफरेंट टाइप के डिज़ाइंस के अंदर कैटेगराइज कर सकते हैं या डिवाइड कर सकते हैं. मैट्रिक्स सिस्टम कुड बी डिफ्यूजन बेस्ड डिज़ाइन, it could be dissolution based design, it could be erosion based design, or a combination of diffusion and dissolution. So we'll be discussing all these designs in detail. This is the diagram which is showing you the difference between the diffusion based design, diffusion based matrix system, and dissolution or surface erosion based matrix system. In diffusion based system, the drug is present in a carrier matrix and the dotted line shows a depletion zone over here for the diffusion of drug from its carrier matrix, whereas in dissolution or surface based erosion matrix system, the drug is dispersed in a carrier matrix, and this line shows the dissolution zone where the drug is being released from this carrier matrix after getting dissolved in the surrounding environment. Let's begin the discussion of diffusion based metric system. In a diffusion based design, the release of the drug is mainly influenced by the diffusion properties of the drug in the matrix. In contrast to a dissolution based metric system, the matrix itself is inert and does not dissolve nor degrade in the dissolution medium. This means that the dimensions of the matrix do not change during the release of the drug. Fick's law of diffusion describes diffusion process of the molecules in the matrix, and it was derived by Adolf Fick in 1855. For steady state conditions, the diffusion process is described by Fick's law of diffusion, which states that the drug in a solution passing a unit area is proportional to the concentration difference over this unit area. I'm repeating it again. For steady state conditions, the diffusion process is described by Fick's law of diffusion, which states that the drug in solution passing the unit area is proportional to the concentration difference over this unit area. This can be described by this equation, which says that J is equals to minus d dc over dx, where J is the flux which is measured in kilogram per meter square per second, whereas dc over dx is the concentration difference, which is expressed in kilogram per meter power 4, and d is the diffusion constant, which is expressed in meter square per second. For non-steady state diffusion, Fick's law describes how diffusion causes the concentration to change with time. This can be expressed by this equation, which is in literature two types of metric systems. In literature, two types of metric systems are generally mentioned, that is homogeneous metric system and porous metric system. Before going into detail of these homogeneous and porous metric system, let's repeat the discussion that we had done about the diffusion based metric system. डिफ्यूजन बेस्ड मेट्रिक सिस्टम में रिलीज ऑफ ड्रग मेनली इन्फ्लुएंस होती है बाय डिफ्यूजन प्रॉपर्टीज़ ऑफ द ड्रग इन मैट्रिक्स, यानी ड्रग अपनी कौन सी डिफ्यूजन प्रॉपर्टीज़ या कैसी डिफ्यूजन प्रॉपर्टीज़ मैट्रिक्स में शो कर रही है, ये डिटरमाइन करेगी ड्रग की रिलीज रेट को. मैट्रिक्स इटसेल्फ इनर्ट होता है और वो डिग्रेड नहीं होता डिसोल्यूशन मीडियम में. इसका मतलब ये है कि जो भी डायमेंशंस हैं मैट्रिक्स की वो चेंज नहीं होंगी ड्यूरिंग द रिलीज ऑफ ड्रग. फिक्स लॉ ऑफ डिफ्यूजन प्रोसेस को डिस्क्राइब करता है मैट्रिक सिस्टम में, जिसको सबसे पहले डिराइव किया था एडोल्फ फिक ने इन 1855. फिक्स लॉ ऑफ डिफ्यूजन दो तरह की कंडीशंस के अंदर ड्रग के डिफ्यूजन प्रोसेस को डिस्क्राइब करता है, एक स्टेडी स्टेट कंडीशन में और दूसरा नॉन स्टेडी स्टेट कंडीशन के अंदर. स्टेडी स्टेट कंडीशंस के अंदर डिफ्यूजन प्रोसेस जिसे फिक्स लॉ डिफाइन करता है वो ये कहता है कि डिफ्यूजन स्टेट करती है दैट द ड्रग इन अ डिसोल्यूशन पासिंग अ यूनिट एरिया is proportional to the concentration difference over this unit area. और इसे हम डिस्क्राइब कर सकते हैं इस इक्वेशन से, विच इज़ J इज इक्वल्स टू माइनस डी डी सी ओवर डी एक्स. इन नॉन स्टेडी स्टेट कंडीशन के अंदर फिक्स लॉ ये कहता है कि कंसनट्रेशन डिफ्यूजन causes the concentration to change with time. which can be described by this equation, which says that partial derivative of c over time is equals to d partial derivative square of c over partial derivative of x square. This is actually the concentration difference, which is changing with the time according to the Fick's law in case of non-steady state. Types of diffusion matrix. The first type is homogeneous matrix. A homogeneous matrix system, the drug is either dissolved or dispersed in a homogeneous matrix, mostly a polymer. Once the matrix system is immersed in a dissolution medium, the drug present at the surface of the matrix will dissolve in the dissolution medium. This will result in a concentration difference, and the drug will diffuse from the inner layers to the outer layers of the matrix. As a result, a depletion zone will be formed at the boundary of the matrix, which increases in time. Because the drug has to diffuse over a longer distance, the release rate will also decrease with time. The release of a drug from a planar metric system under sink condition was described by Higuchi in 1961, and he gave this equation to describe the release of a drug from a planar matrix, which says that Q is equals to M over A is equals to under root of this C naught minus Cs multiple of 2 dCst, and this equation can be expressed in terms of time as well, where Q is the amount of drug release per surface area, and this amount of drug release per surface area can be described as this equation, which is D is equals to diffusion coefficient of the drug, C naught is the initial total drug concentration in the matrix, and Cs is the solubility concentration of the drug in the matrix, and T is the time. This equation can be further simplified to dq over dt is equals to k under root 1 over t. It shows that the release rate is inverse proportional to the square root of time. If the release rate is plotted versus the square root of time, a straight line is obtained. सो होमोजीनियस मैट्रिक्स सिस्टम में ड्रग को हम या तो डिज़ोल्व करते हैं, डिस्पर्स करते हैं इन मोस्टली विद अ पॉलीमर. वंस ये मैट्रिक्स सिस्टम किसी भी डिसोल्यूशन मीडियम में इमर्स होता है तो ड्रग जो सरफेस पे प्रेजेंट है मैट्रिक्स की वो डिज़ोल्व होगी डिसोल्यूशन मीडियम में, और एक कंसनट्रेशन डिफरेंस एग्जिस्ट करेगा ड्रग की इनसाइड और आउटसाइड लेयर पे, और ड्रग from the inner layers diffuse होगी to the outer layer of matrix, जिसकी वजह से एक डिप्लीशन जोन फॉर्म होगी at the boundary of the matrix, जो इंक्रीज होती जाएगी with the passage of time. इस रिलीज ऑफ द ड्रग को जो प्लानरी या प्लेनर रिलीज हो रही है प्लेनर मैट्रिक्स के अंदर, इसे हिगुची ने 1961 में डिफ़ाइन किया था, और इस इक्वेशन से डिफ़ाइन किया था कि अमाउंट ऑफ ड्रग रिलीज इज इक्वल टू द अमाउंट पर स्क्वायर सरफेस एरिया ऑफ द ड्रग रिलीज. दिस इज m over a, and this can be expressed by this equation which is defined over here, and this can be simplified to dq upon dt, which shows that the release rate is the inverse proportional to the square root of the time. If the release rate is plotted versus the square root of time, a straight line is obtained. The second type of matrix based system is called as porous matrix system. A porous matrix system is actually a variation of a homogeneous matrix system. In this case, the drug is dissolved in a porous polymer, Once the metric system is immersed in a dissolution medium, the pores will be filled with dissolution medium and the drug will dissolve into the filled pores of the matrix. Besides the solubility and diffusion coefficient of the drug in the release medium, also the shape and volume of the pores in the matrix are of importance. Under sink conditions, the release rate can be described by this equation, which is dq over dt is equals to 1 over 2 square root 2 c naught minus epsilon cs multiplied by epsilon dcs divided by tortuosity and time, where this expression is shown you as the tortuosity and epsilon is the porosity of the matrix. Here tortuosity is defined as the dimensions and branching of the pores in the matrix. पोरस सिस्टम होमोजेनियस सिस्टम की वेरिएशन है। इसके अंदर हम ड्रग को डिसॉल्व करते हैं एक पोरस पॉलीमर में, और जैसे ही मैट्रिक सिस्टम इमर्स होता है डिसोल्यूशन सिस्टम में, तो ये पोरस पॉलीमर्स पोर्स फॉर्म करता है। डिसोल्यूशन मीडियम इस पोर्स में फिल होता है और ड्रग को रिलीज़ करवाता है आफ्टर फिलिंग इनटू द पोर्स। Besides solubility or diffusion coefficient of the drug in the release medium, shape or volume of the pores in the matrix important. Under sink conditions, the release rate can be described by this equation, where the main important thing is the tortuosity and porosity of the matrix. यहाँ पर tortuosity को अगर हम define करते हैं तो we say it as the dimensions and branching of the pores in the matrix is the tortuosity. There is another thing which is described in the metric system, that is power law equation. It should be noted that the Higuchi equations are only valid for matrices that are inert to the dissolution medium. So if the matrix swells, dissolves, or if the diffusivity changes in times, the Higuchi equations are not accurate anymore. In order to predict the release from these systems, Corsimer and Pepaz in 1983 derived a simple relationship also known as the power law, which is Q over Q infinity is equals to KTN, where Q is the amount of the drug released at time t and Q infinity is the amount of drug released at infinite time, and N is equals to diffusional exponent. Higuchi equation उस वक्त तक वैलिड है जब matrices inert हैं to the dissolution medium. अगर matrices inert नहीं है to the dissolution medium और matrix swell होता है और dissolve होता है और उसकी diffusivity change होती है with time, तो Higuchi equation accurate measure नहीं होती ड्रग की release को define करने के लिए. In order to predict the release from these systems जहाँ पर matrix खुद swell हो रहा है और वो inert नहीं है, कॉर्सिमेर और पेपाज ने 1983 में एक सिंपल रिलेशनशिप डिफाइन की थी जिसे हम पावर लॉ कहते हैं, और इसे हम इस इक्वेशन से डिफाइन कर सकते हैं, विच सेज दैट Q over Q infinity is equals to KTN, जहाँ पर Q is the amount of drug release at time t है और Q infinity is the amount of drug release at infinite time है, which is because of the swellability of this matrix polymer, and N is the diffusional exponent. So that's all from today's class. For your questions and queries, use your HOLMS portal. Thank you for patiently listening to this lecture.